Welcome to Rich Planet TV. Now, I mentioned in my last video that I was working on an energy project and I want to document what I've done and what I'm going to build, because what I'm investigating here is the subject of free energy, which is a controversial subject. Perhaps some refer to it as over-unity devices or perpetual motion machines. And there is a lot of information that you can find. I mean, one publication is by Patrick J. Kelly, who has documented a lot of the claimed over-unity devices, and his publication is a practical guide to free energy devices, and it runs to almost 1,000 pages. This is the 2020 edition. Now, I did discuss the subject of alleged free energy on Rich Planet many years ago, 2010, somewhere around there. And I did set up a study group in 2015 where we looked at many of the devices in Kelly's document to try and identify which ones we think may actually work, may actually produce more energy out than in. Now, you say that to a physicist, they will immediately say that that's impossible. It breaks the first law of thermodynamics. No closed system can output more energy than what goes in, right? But some of these devices are alleged to be tapping into a source of energy which is as yet not fully defined. Energy from what's known as the quantum vacuum. Energy from within the fabric of space itself, according to some, is able to be extracted. So in that case, if that's proven, you would need to modify that first law of thermodynamics to say something like the total amount of energy in a closed system will remain constant unless energy is extracted from the vacuum. And this is the whole controversial thing about this subject. And if you go online, you'll see many of these devices discussed with lots of interesting debates, and a lot of people who come from the mainstream science, standard physicists, will say, well, no, that's not possible. But one comment I would make is that the vast majority of people who you will see discussing these types of devices online, very few of them actually go and build one. And that's the only way to look into whether they work. You can present as many equations as you like and state as many laws as you like, but the proof of the pudding is in actually building and testing something and see if it does break one of the holy laws of physics, which some of these devices are alleged to do. Now, I'm not saying that any of them work, but I have looked at the field, and it is a huge field. There's all different types of devices. One thing I would say that a lot of them, a very high percentage, involve magnetic fields or magnets or magnetic coils. So putting energy into a magnetic field and then taking energy back out of a magnetic field using a coil or a permanent magnet. And it is that exchange of energy, because when you put energy into a coil, for example, that energy is stored in space around the coil. And then when that magnetic field collapses and the energy comes out of the coil, it's being extracted from space. And the claim is that if under the right conditions, you can more energy can be extracted from that space, which is coming from the energy which is inherent within empty space. Like I say, I don't know that it's true, but I'm very interested to find out, and I have been for many years. And I did experiment with some Stan Myers. This is the Stan Myers water fuel cell that I built some time ago. I didn't really get very far with that. That's shelved at the moment and has been for many years. Now, one of the machines that I think because I did look at a lot of these machines many years ago, and the one that stood out for me and always has is the homopolar generator. So there are two engineers who have made homopolar generators, and both have demonstrated them to independent examiners, and as far as I read it, both have demonstrated that there's more energy coming out than going in. And both of these researchers were qualified electrical engineers, and the interviews that I've seen with them, they seem very clued up and their claims seem genuine to me. So the first one is Bruce De Palma, who his machine was called the N machine, which was a homopolar generator, and I will explain the principle in a minute. And the other guy was a guy called Adam Trombley. I know that Bruce De Palma is no longer with us. I'm not sure if Adam Trombley, both American, I'm not sure if Adam Trombley is still alive, and I think he worked with a guy called Kahn. Now, Trombley's device was more expensive than De Palma's. It seemed more sophisticated, and I'll explain that in a minute. But they were both using exactly the same principle. And let me just tell you what happened to them. Bruce De Palma, he was threatened, or he alleged that he was threatened by an Apollo astronaut, Dr. Edgar Mitchell, apparently approached him and said, if you continue experimenting with this equipment in California, you're going to get your head blown off. And I have read recently that De Palma's N machine was taken over by the military. Now, Adam Trombley, with his machine, he was asked to demonstrate the device at a demonstration at to the United Nations. So he took his device there, and there's a video of him explaining this. He took his device there, and when he got there, he was expecting sort of a massive lecture theatre with 400 seats or whatever, with a nice lab, to be able to demonstrate his over Unity machine. They told him, well, we're not going to have it in this place. We want you to do, there's a church around the corner. And they made him take it to this church where there was a very small audience, only about 40 people. He demonstrated it there, and he was then asked to take the device to the White House to do another demonstration, which he did, and then apparently it was taken over on grounds of national security. And now I actually spoke to Adam Trombley, I would say it was around about 2010, maybe a year either side. I rang him up because I was fascinated by his devices, and I just wanted to speak to him. I didn't do an actual interview where I put it out on Rich Planet, but I remember him telling me that story, and I remember him telling me that they came and confiscated equipment from his lab as well. So this is why I lean towards that device, because De Palma and Trombley, they weren't working together. They were both independently looking at homopolar machines, and they both said that these can produce more energy out than in, and that energy is coming from the quantum vacuum, or whatever you want to call it. My life's had some changes in it recently, as you all may well know, and I've not really felt that motivated to do new films, certain projects. However, I am spending a lot of time in the house, and I've always wanted to try and investigate the homopolar generator claims, because I think that would be the biggest chance of success. It's not a particularly complicated machine, and I think it's due to Trombley and De Palma that the reason why I want to investigate this, because I think they were genuine guys. And De Palma had Stanford University come to his lab, and they said it was generating more energy out than in, and they didn't know where it was coming from. All right, so So what I wanted to do, because I am building a device and I want to document it on video so people can see and build one themselves. So if we just first, I'll just explain the principle. So in a normal electric generator, it follows Fleming's right-hand rule. where you have 3 vectors at 90 degrees to each other. And if you do this with your fingers, you point them all at 90 degrees to each other. The forefinger is the field, the magnetic field. The second finger is the electric current, and the thumb is the motion. So if you move something through a magnetic field which is running that way, you get electricity induced running that way. And this is how all electric generators work. Now, in a standard electric generator, generally the electric current will be running in parallel, because you have, as you all know, in your washing machine or your lawnmower or whatever, you have something which is spinning round on an axis, right? And usually the electric current is running along that axis, back and forwards around it like that. So your second finger is the current, your thumb is the motion going around. So the field is at 90 degrees going through the axis of that it's spinning on. With the homopolar generator, this is all shifted through 90 degrees, right? So your current, your second finger, your current, which normally runs along the axis of rotation, right, points outwards from the axis of rotation, right, which is in the form of a disc. So I've got 2 copper discs here, which are 5 millimeters thick, and they're 180 millimeters in diameter. Now, this is what I'm using for my copper disc. So what I've called it is a mini end machine. It's a mini version of what Bruce De Palma built, and I'll explain why I've chosen to build a smaller version of it in a moment. But the principle is that the reason why I'm using 2 discs and not 1 is because 10 millimeter thick copper cost a fortune to buy, right? So I could only find 5 millimeter thick at a decent price, right? So these are going to be screwed together. So it's effectively a 10 millimeter thick solid copper disc, right? So that will be, the intention is to spin that as high as you possibly can. The faster the better. If we can get it up to 3,000 RPM, great. If we can get it to 6, great. If we can get it higher, even better, because the voltage produced is proportional to the speed. All right. So you have a magnetic field which is going to go through the disc as it's spinning, and what results then is a voltage between the center of the disc and the rim of the disc. So the shaft that you put on the center, you have to have a brush system which will take the electric current from there, and you have another brush on the outside of the disc which takes it from there. And typically these sort of systems, you're lucky if you're going to get 1 volt between the center of the disc and the outer side of the disc. Well, what's the point of that, you might think? Well, 1 volt but at a very large current. And this is why these devices are not used, because you've only got 1 conductor in your motor that the electricity is being induced in, which means normally you would have a coil, but due to the configuration, you can't make a coil in this configuration. So you're left with extremely small voltages, but a high current, which is useless. You can't use it. For example, let's just take your microwave oven, for example. It's 750 watts. So if you wanted to power your microwave oven off 1 volt, you would need 750 amps, which is, it would be a cable like that. So let me just explain what De Palma and Trombley did. So De Palma, he used, on his copper disc, he used permanent magnets on both sides. So you would have the north side on one side and south on the other. So you've got the magnetic field running all the way through the disc. And with Trombley, his device was more sophisticated. Trombley used electromagnets, so he had several electromagnets all the way around the disc on both sides. Now let me just point out that both of them used co-rotating magnets, and this is a very important element of this as to why I think it achieves over unity, if indeed it does. Normally, you would have something generating the magnetic field here, which is fixed, and the disc would rotate. So you'd have an air gap, a gap between the magnet, which is stationary, and the rotating disc. But both Trombley and De Palma, what they did was they fixed the disc, they fixed the magnets to the disc on both sides, and they spun them together, co-rotating at the same speed. Now, intuitively, you think that that wouldn't produce a voltage because there's no relative motion between the disk and the field, right? But apparently it does produce a voltage. And by fixing the magnets to the disk, what that does is it gets rid of the air gap. And the air gap itself is what reduces the size of the magnetic field because it's a higher reluctance path. So by attaching your magnets, whether they be electromagnet or permanent magnet, to the disk and rotating the whole thing, it improves the efficiency of the machine because your magnet is right up against the conductor. Now, Trombley went a step further because if you've got a magnetic field going through this copper disc, we all know the shape of a magnetic field. If you get a bar magnet, it goes up, comes out of the magnet, it goes back round, and then it goes back in like that. So it's circulating in 3 dimensions all the way around. It's doing this, right? Now, when the magnetic field is going through the air, the size of that field is reduced because air has a very low magnetic permeability, right? If you encase that field in a highly magnetically permeable material, it reinforces that field and it makes the field stronger. So what Trombley did with his device, so he had several electromagnets on each side of his copper disc, and then he encased the whole thing in a magnetically permeable material so that the field generated by the electromagnets was then captured inside the ferrite, highly permeable magnetic material, and then fed back round. So you've got if you imagine a field going round, all the way around, and it's outside the disc and then inside the disc. But when it comes outside the disc, it's been given a much less reluctance path, right? So that increases the strength of the field within the disc. Now, when I spoke to Trombley, he told me that one of his devices cost him over $100,000 to build, and you can understand why, the complexity of that, because the electromagnets are spinning round, so you've got to have a brushing system to get the electricity onto the thing. You've got to have brushes for the shaft, you've got to have a brushing system for the disc, and then you've got to build all of this ferrite material around it, and then you've got to get it all spinning at as high speed as you can. And I think his machine was something like this sort of size, size of this table maybe, and I think it had a cast iron sort of bed, some sort of machine bed. So yeah, that cost quite a lot. And De Palma's some of his devices were quite big as well, this sort of size. There's one video where the actual magnets and the rotor are being lifted onto the bearings by a small crane. Now, I thought I would try and keep it simple. So I would use permanent magnets and not electromagnets, because then you haven't got to use brushes to power the magnets, and also build it slightly smaller. Now, obviously, if you build it slightly smaller, the voltage that you get isn't going to be as high. But the development in magnets over the last sort of 10 years, there's been quite an improvement in the performance of magnets, and you can now get neodymium magnets, which are much stronger magnets than you used to be able to get, right? So I'm having 2 magnets specially manufactured in China, and they are N56, which is the latest, highest strength magnetic material. So I'll be working with a material that Bruce De Palma didn't have access to, and the voltage output is directly proportional to that magnetic field strength. So if my magnets are twice as strong as De Palma's, it means that the voltage output will be twice as much. And also the speed. The voltage is directly proportional to the speed of this disc is going at. Now, if I make the disc smaller, obviously it's going to be a slower speed. But there are motors that can possibly, if we get the bearings right, we could try and get it up to beyond 6,000 RPM, which is sort of the area that De Palma was in. Okay, so that's, obviously I haven't given you all of the details there because I've had to make various calculations and other things. This video is more for public consumption rather than an engineer's consumption. So I'm just going to go through some of the parts that I've been working on, because I want to show them now, because I don't want to just produce the finished thing and say, hey, this is what I built, because no one will believe that I've built it. All right, so I'm going to show you the bits that I've ordered. So this was the first thing. 2 copper discs, solid copper, which are they're 180 millimeters in diameter. And as I say, I'm going to fix them together and screw them together. We'll just put them there. Okay, now, so I'm going to go through some parts now. Now, the first thing is this, which is obviously you need a good base for something like this. Somebody did suggest to me that I could use a milling machine table. I did look at that, but I thought, no, I'll go for a solid steel. So this is 20 millimeter thick steel, and I think it's 320 millimeters. So it's just over a foot square. And I've had this machine drilled and tapped. So, which way around does it go? Yeah, okay. So on this is going to be a mounting block with a bit cut out of it. And then there's going to be bearings on top of that mounting block. And then obviously a copper shaft. And this will be fitted to that shaft. It's called a press fit. So I'll just get this bit that I've had made. So I've been using a local engineering company who've been doing some bits and pieces for me. I've been giving them my drawings and getting bits, getting it made in stages, really. So this started off as just it's a 6-inch square piece of tube, steel tubing, which started off, it was a meter long. Had to buy a meter long piece, so that I've cut that off to be the same size as the base plate. That goes that way. So I've got 6 M8 holes drilled in here all the way through, and 6 holes drilled in here. So that goes on there. And I've got some bolts here. So you can bolt this to the base plate. So that fixes there. And obviously the discs are going to sit in there and whiz around very, very fast. Now you notice here that it's slightly lower on one side. So I got them to cut a bit out here and lower that. You know, you'll see why in a minute why that bit's been lowered. So I've had holes cut in here. That's for the bearings. So there's a bearing goes there, a bearing goes there. If you don't know what a bearing is, there's a shaft going to go through there, and they allow the shaft to spin, right? So there's going to be a copper shaft about that long, varying different widths, right? So it's going to be 12 millimeters in diameter here, and then it's going to go up to 20 millimeters, and that's to accommodate what's called a press fit, to fix the disc onto it. And there's an electric motor going to go here, a brush system going to go here. Now the magnets are going to be slightly smaller in diameter to this disc, made of N56 neodymium. So I think they're going to be 176 millimeters in diameter, right? So I'm having some small holes drilled, 6 holes drilled all the way around here, and the magnets are going to have the same holes in them. So I've got some small bolts, which are going to hold the magnets on. Now the magnets are 20 millimeters thick each. So you're going to have one magnet there and one magnet there, and they're going to be bolted together. So you've got the copper disc there with 2 magnets, one either side, with a shaft going through, and an electric motor here, which I'll just get the electric motor. So there's a mounting block for the motor, and I've got them to drill the holes to line up with this mounting block. There's a couple of screws missing there, but that goes in there. Now this motor, okay, so you can picture it there now. That's going to spin round mega fast with a rod going through there, which this disc's going to be on with the two huge magnets either side. And here's going to be a brush system where it's going to take the voltage from the actual shaft, from the rotor. And there's another brushing system which is going to butt up against the outside of the discs. All right. Now this motor is from a CNC machine, which you can buy fairly cheap, and it comes with its own power source and control system. It's a 3-phase pulse width modulated motor. That's this power supply. You can see that. It's just a 240 to 48 volt power supply, and then it comes with this control unit. All right, now attached to this control unit you've got a potentiometer, a control knob, and that changes the speed of the motor. And this is advertised to be able to go up to 20,000 RPM. 20,000 RPM. Now, whether I'll be running it at that speed, I highly doubt, but I'm hopeful I can get it up to at least 3,000 RPM. And the other thing I'm not certain about is whether, because this is a 400 watt motor, whether that's going to be able to produce enough torque to get these two large magnets spinning. It may well be that this motor, there isn't enough power in order to turn the disc system, in which case I'm going to have to get a larger motor, cut a piece out of here, and mount a bigger motor on there. But I thought I'd start with a small one, keep the price down, because if this can turn the thing, then we're laughing, really. Now, I mentioned the brushing system. Does anyone recognise what this is? That goes on there. All right. That is a starter motor from a Ford Transit van. Right. Now, the great thing about a starter motor is, that's the motor in here. That's just a big switch there. Then that's the bit that this spins round, and that's the bit that turns your engine when you start your car. So this is quite a big one. It's 2.2 kilowatts, and I've got a big one for a reason, right? So this, the actual motor, that's magnetic. I can feel the magnetic pull in there, right? So that's there's a brushing system in there, all right? So what happens is, from your car battery, you have the negative and the positive terminal go on there, right? That then, via this commutator, turns your starter motor, okay? And you can see the diameter of that commutator is 32 millimeters, right? But this brushing system here is designed to take 200 amps. So the negative and the positive. So if I were to take that off there and put it on the end of my copper shaft, copper rotor, I can common them up, because I'm not using a commutator, I'm just using a solid disc, right? So if I common the positive and the negative, I'll get 400 amps, right? So these 4 brushes, they're 100 amps each, right? And this comes off. I should have unscrewed it to show you, but that will screw off there, and those discs will mount on the edge, on the end of my copper shaft. And this is why I've lowered this side, because it needs to be able to house that. So I bought this. I'm going to chuck most of it out. I only bought it to get the brushes, right? So this is just a little bracket here, and that will sit there, and the brushes will go in there, and then this will fix it on the end of the shaft. So the shaft will have a slightly larger diameter, 32 millimeters here. So it's going to start with 10 millimeters into the collet, and then it'll go up to 12 millimeters for this bearing, and then the shaft will then go up to 16 millimeters, all right, which will be press fit onto this disc, and then it'll go up to another 20 millimeters through here, and then up to 32 millimeters for the brushes. So the copper rod arrived the other day, and I'm having that machined now, so I should have that. And once I've got the copper rod, I need to obviously fit the rod all the way through, but also these are going to need small shims underneath them so that everything's the right height, right? And get that nicely all level, and then I'll be able to start running the motor without any discs attached or any magnets attached, because I want to do quite a lot of tests. What I want to do is set the brush system up on the end and see how much load there is on the motor. So take it through from 0 RPM up to as fast as I can get it with just the rotor, and see how much energy is used in just overcoming the friction from the brushes. Now, with regards to the magnets, I researched UK companies that can manufacture specialist magnets. I found 4, and I had quotes from 3 of them, and they were pretty expensive. You're talking thousands of pounds. So what I wanted was a neodymium magnet, the size of that disc, but thicker, about 20 mil thick, with holes in it. And yeah, they gave me some quotes. So what I did was, there's a company in China, and I just submitted an email to this Chinese company that make magnets, and they came straight back with a price which seemed okay. So I've sent them the drawings, and there's a month lead time on that, so I'm waiting for the magnets to come. And when they arrive, I've got to be very careful with them, because these are the strongest magnets in the world, and they're going to be like that. So it's going to be fun trying to assemble it with such strong magnets. They're going to want to stick to everything. Yeah. So that bit will be fun when I unwrap these. I mean, I would imagine they're going to have to send them separately, and also like in a big package. Otherwise, it goes through the post. Things are going to be sticking to them. What I've done is I've designed a control panel, which will have all of the controls for this motor, but it will also have it will take the output from the brushing system on here and put it through a load. Now, I won't go through the physics of the actual loading system, but basically it has to be very, very low resistance, because I don't know what voltage I'm going to get out of here. I don't know whether it's going to be half a volt, 2 volts, a quarter of a volt, 5 volts. I don't know. I mean, obviously, the higher the voltage, the better, because it makes the circuit much easier that you're going to load it with. And I don't necessarily expect the input power of this to be less than the output power that I'm going to drive, right? But what might be interesting, let's say you've got this running at a certain speed, 1000 RPM, and it's generating 1/10 of a volt or whatever. It's generating so much power. You increase this by, let's say, 50 watts, but the output power goes up by 70 watts. You increase this by another 50 watts, and the output power goes up by another 70 watts. So you get an additional power, even though the total the total out isn't more than the total in. So I think that hopefully it will be able to demonstrate whether there is additional energy somewhere along the line. Right? That's my intention with this device. So I'll just show you a few other things that I've ordered. I've got a whole set of drawers here. So what I'm going to do is build a load bank. So these resistors are 0.1 of an ohm, and I'm going to have 20 of those. So I've got panels to mount them on and stuff. So and you'll be able to use them in various configurations of series or in parallel. All right, because if you've only got 1 volt, if you put a 0.1 ohm resistor across it, you're going to get 10 amps, right? So you're going to get 10 watts. If you've got 20 of them, that's 200 watts, right? So you should be able to put a 200 watt load across the 1 volt. And if it can supply the 200 watts, the 200 amps, then I'll be able to order more load, more resistors, and see. Now, obviously, you need to. Obviously, there's a huge amount of current coming off this. As I mentioned, potentially 400 amps through there, and the brushing system. I haven't mentioned the brushing system for the disc. So there's holes in this base plate. All right, so they bolt down onto there, and there's some nylon rods which I've had made. So I've got some nylon rod. Now the reason why these are nylon and not steel is because the brush needs to be isolated from the rest of the thing. Right, so that's going to go there, that rod, and I've had an M5 thread made in there, so that's going to go on there, and then that's the brush. So these are carbon brushes, spring loaded. Right, so that's going to that hole there will go onto that. It's slightly, I need to prise that open with a screwdriver, but that will go on there, and this opens out like that and goes. Where's the disc? So there, your brush there, look, goes on the disc like that. You see there. All right. So this is carrying the electricity off the edge of the disc, and I've got 3 of these brushes, and that's going to be mounted there. And you see it there in between there. If you have a look at the drawings, you'll see it all. So there's going to be a brush there. A brush can go underneath there like that, and another one there. Now I don't know how much friction these brushes are going to cause and how much power that's going to take. As I say, I might need to introduce a bigger motor with this. And what I've done is I've built this little control panel, because this motor comes with an RPM, the control unit here. Where's it gone? Yeah. It comes with an RPM readout, so it tells you how fast it's going, and it's got forward, reverse, it's got a speed controller on it. So all of the controls for that I'm put on this little panel. And this device here, this is a power meter, which is using a Hall effect device to measure the power going into the thing, right? So that will tell me how much power in total the thing is taking. That tells me how fast the disc is going. Start, stop, forward, reverse. There's a warning light there and a speed controller here. So I was just going to put that on there and do some preliminary tests on with just the shaft, because this is just a temporary controller. I'm actually going to build a big panel which is going to fix onto here, onto the back, and it's going to have some isolation switches. These are going to be used to switch the load on, right? So switch. So if you're running it, let's say it's generating a volt, and you want to actually take that power off, you can then switch these, switch the load on, and then according to the Palmer, it should just keep running and supply that current without any problem. But according to conventional physics, what should happen is, as soon as you put that load on, the rotor should slow down, the voltage or the power that the motor draws should go up. It should be affected by adding the load. So that'll be interesting to, once it's running, to introduce various sizes of load at various speeds to see how it affects the input power, to see if the extra load that's driven electrically in the output, is that completely accounted for by whatever the increase in the input is. All right. So yeah. So anyway, this is what I'm working on at the moment, and it's helping to distract my mind from other things. And yeah, this is very early stages. I'm quite excited because I'll be getting the rotor from the engineering company after they've machined it. I'm going to do a load of tests with the rotor on it, so we'll get it whizzing round, and then once that's done, when the magnets arrive, we're going to get the copper disc press fitted to the rotor, and then we'll get it balanced, and then that's going to be some fun, and then hopefully we'll have the whole thing working. All right, but yeah, there's much more to come. Welcome to Rich Planet TV. Now I'm going to make a series of videos showing the progress of this homopolar generator. I showed some of the parts in the last video, and I've put some of them together, painted it, so we've got the two bearings that I mentioned in the last video here, the 400 watt electric motor here, and I took the brush system out of this is a Ford Transit starter motor, so the brush system was on this commutator here, so I've taken them off and they've been mounted on this shaft, so they will attach to the end of the copper shaft, which is going to run through here. Now I've made this little temporary control panel. The reason why I say temporary is because I'm not sure whether this motor is going to be able to provide enough torque to get the two magnets and the copper disc spinning. If not, I'll have to use a bigger motor and modify this section. So I don't want to make a proper control box until I'm certain that these controls are going to be used in the finished thing. So on the control panel, we've got this is just a start button, which starts the thing moving. I'll just power it up. Right. So you can see this display unit here is not part of the motor control system. What this is monitoring the electrical power going into the whole thing. So I'll give a close-up of that in a minute. We've got a warning light here, which is just to do with the motor control. If you pass any of its parameters, like too much, if it can't cope with certain things, it just flashes that light on. This is the start button, so we'll set it spinning. So just got it on a slow speed there. So this here reads out the RPM. Switch it off, you can press that button, that changes the direction. Alright, so I'll just give a close-up of that control panel and also the brush system. So we're running at 1700 RPM there. There we go, 4000 RPM. So that motor is taking 25 watts to turn that motor at 4000 RPM. Obviously it's not driving anything. And if I switch it off, you'll see that just the power supply alone, which is here, is taking 10 watts. So this panel is going to be really useful when the thing is finished, in order to know exactly how much power is being used by the whole system. Now I'll just get a close-up of the brushes. So we've got a brush here, a brush here, a brush here, and a brush here. They're made of carbon, and you can see they've all got quite thick cables coming off them. So I've just put a nut temporarily just to hold the brushes out, and what will be coming through there is the end of the copper shaft, which will be 32 millimeters in diameter, and then off of these brushes, they're 100 amps each. I've got 100 amp wire, and then it will be common to 350 amp wire. Okay, so I've got various sizes of cable in this project. This is the 350 amp cable, so we'll have these four brushes that I just showed you will be connected to this cable here. You can see that's quite thick. That's 350 amps. So that's one. That's your negative coming off there. This is the positive cable, and that will be attached to the brush that's going to be rubbing up against the disc. So we've got a positive and a negative. like I say, in the order of 1 volt, but hopefully 200 to 300 amps. I've got that will then go to a resistive load, which is going to consist of 20 0.1 ohm resistors in banks of 5. So that's 4 banks of resistors. So they'll need 100 amp wire, which I've got. This is 100 amp wire here. So that wire will lead to each of the 4 banks of resistors. And then I've got some 30 amp wire for the actual resistors, which is there. Which is the thing with this project. You've only got 1 volt. In order to get the power out, you must accommodate it through the right size cables. Otherwise, you're not going to get anything. So I'll just show you what I intend to do with the load banks. So I've got some Perspex panels here, and what they're going to do is just, well, I haven't peeled that one off yet, but I'll just demonstrate it with one of them. We've got heat sinks. They will go on the panels that way, and we've got our 0.1 ohm resistors. They will be mounted on there, and then there'll be terminals on here coming off. Now, I do intend to make a more sophisticated control box, which I'll either put here or, well, I'm not sure where I'm going to put it, but I'll show you that now. Just an empty box at the minute, and what we're going to have there is, what I'll do is I'll do a close-up now so I can show you. So on this control panel, I'm going to have all of the controls that's on here. So there's a speed indicator, start and stop, and a speed power input. I'm also going to have two load bank switches. These are huge switches, which will, 2 of them will go there. These are 200 amps each. So I'm going to put them in parallel so I can feed 400 amps through to the load bank. So on the top here you'll have your negative terminal. So that's the negative that will come off there. The positive terminal, which will come off the brushes. And then this will be what you switch output. So there'll be a switch. Those 2 switches will connect those 2 together, and these 2 will be connected to the load bank. Very important, I've also got, there's a voltmeter going to go on there, so that'll tell me how many volts the generator's putting out. And I've got some nice labels done here, so that'll go underneath the voltmeter, voltage output, the start and reverse buttons, load bank, speed control, that's the warning light, that's the rotor RPM, so that'll go underneath the speed meter. Electrical input, that'll go there, and then that's just a label, mini end machine control panel. Right, so that should be a useful tool in just doing tests and running the machine up to certain speeds, looking at the power input, and then seeing what voltage we've got coming out, and we will know the power output by virtue of the fact of whatever load we've got over that voltage. So I spoke to the engineering company today who were making the copper rotor, and they've had a problem. They had an outage or something, so that's been delayed. But hopefully tomorrow I'll get the shaft made and get that fitted, and I might take my camera along to the company just to take some shots. So I really have no idea as to whether this is going to show that there is extra energy can be generated with a homopolar generator, because part of me says there's no way it can be true, because someone would have seen Trombley and De Palma's work and they would have just done what I've done here, and they would have demonstrated it. The cat would have got out the bag and people would be running their homes off it or whatever. It's too much of a simple piece of technology to be able to hide. But then another part of me says, no, they didn't threaten De Palma with a bullet in his head for no reason, and they didn't take these devices off them for no reason. So it's a real mystery. It's a real mystery, and I have got no idea where the answer lies. So if I don't find 1 extra watt of power comes from this homopolar generator, that all of the, in other words, that the when you load the system with the electrical load, that load is exactly reflected at the input power, which is what, you know, a standard physicist would say, then I will debunk the whole concept. But we'll see. We'll see. The proof of the pudding is in the making of the machine, as I said in the last video. And it's interesting that I mentioned Fleming's right-hand rule in the last video, where this is the principal of operation, Fleming's right-hand rule of this machine. So the forefinger is your field, your magnetic field, which is going to go that way. Your second finger is the current, which is going to go out to the rim of the disc, and the thumb is the motion. Okay, so perhaps this can become the Rich Planet greeting sign, a bit like Spock, who used to have this as his greeting sign, and he used to, I can do it with my left hand, but not my right hand. He used to say, "Live long and prosper." So it would be, believe none of what you hear, question everything you see, because the truth is over here. Welcome to Rich Planet TV, another update on the Mini N machine. Now, I've moved the equipment up into the office, and as you can see, I've now got the copper shaft back from the engineering company. So they've machined 32mm section here, a 25mm section there, 20mm section, and a 10mm section. Now, originally, I did have this section here was 12mm up to there. And the engineer pointed out that because copper is quite a soft metal, with it being that thin, under the weight of the discs, it might bend the shaft. So I've increased this to 20mm, 25mm. So these are different bearings now. We've got a 20mm bearing and a 25mm bearing. And this shoulder here, which goes from 25 down to 20, that's where the hole in the copper disc is going to butt up against there. And this small section here, I can feel it there with my finger, that's slightly more than 20mm in diameter, and that's to accommodate the press fit when the copper disc is mounted onto the shaft. Now, I was discussing the project with a chap who's quite well up on physics, and he made a very good point. He said that because you've got a magnet next to a large block of steel, you're going to get eddy currents in this steel mounting block. And what will happen is those eddy currents, all right, produce their own magnetic field, which will oppose, they'll provide an opposing force to the magnetic field from the discs. So it's going to slow the whole thing down. So I've decided I need to rebuild this part, this mounting block, and make it out of wood. I don't think there's any other option. I do think, because we're going to have, these are the strongest magnets in the world, and they're only going to be 15mm from this mounting block, and they're going to be traveling very, very fast. So the eddy currents are going to be huge. Now, additionally, these two bearings are made of steel, and again, the disc is going to be quite close to them. And you can get thermoplastic bearings, so I'm probably going to replace these two bearings with plastic ones as well. But, you know, it's 2 steps forward, 1 step back. It's slow progress. Let me just show you it's spinning. It's not mounted on here properly. It's not balanced. I haven't got any shims under here. The bolts aren't in, but it'll still spin. Let's have a look. There you go. It's whizzing around there now at 1700 RPM. And that is drawing 60 watts. So 59 watts. Yeah, like I say, none of it's been aligned. That's quite a few more watts than just the motor. Obviously, it's overcoming the friction in these bearings. I haven't got the brushes on either, nor the brushes for the disc. So, like I said in the last video, I hope this motor is going to be beefy enough to be able to turn these 9.5 kilo discs. But we'll see. I may well have to modify this section and add another motor, as I said in the last video. So I've got some wood here. that I'm going to make a new mounting block with, and I'm not just going to make it as a thin tube like this one. I'm going to reinforce it with some wood so it's nice with sections like that in the corners, so it's nice and sturdy. So obviously wood's a lot flimsier than steel. And the other thing I'm going to do, this height here, this is going to come up a few inches, so the disc height is going to be maybe about there, and that's to ensure that this base plate isn't too near the magnets as well, because we could get, if it was down there, there's going to be eddy currents in the base plate which are going to affect the disc. So just trying to keep any metal away from the spinning magnets. So the next video I should have the new mounting block ready. Alright, so that's the new mounting block made out of wood. I've only just cut the pieces so you can see it there. So I now need to sand them all down and screw it all together. You can see there that it's a good bit higher than the other one, the original one, but it should perform the same function. I've made it so that I can use the same tapped holes in the base plate, so I've got this bolted down now, and these pieces will go on the sides like that, with the top on there like that, and I've also got pieces to go on there as well. That's the new mounting block, and I've added the brush holders as well, so you can see that's one there. There's my boiled eggs. As you can see, I've painted it. And I've also decided to change the way that the brushes are mounted on the outside of the disc. You can see here I've made two of these pieces, and they're going to screw on to there, and I've put two rods through the mounting block, and they're going to fix on there. So the brush will be mounted on here and attached to the disc, and I'll be able to adjust the height of the brushes. Round about there is aligned to the centre, but I will have some adjustment there. And obviously there's going to be another one on this side as well, so you'll have a brush either side. And these rods that I've pushed through the actual structure, they're making the thing a little bit more sturdy as well. I've finished assembling these brush holders. So we've got the frame, the nylon rod. This is the brush, just going to rub up against the disc. So you can see these are spring loaded, so they will open out like that and connect to the disc. Another one on this side, and there's another nylon rod underneath the discs. So there it is there. There's one in the bottom. So we can have a pair of discs on there as well. And I think potentially you could use all 6 brushes, or just have the 4 brushes on either side, or just 2 underneath. I don't think you could use just one on the side, because it might push the thing over. I'm not sure how many pairs of brushes it will need. It may be that I just need one underneath to get the amount of current off that I need, but obviously I'll try it with different combinations of brushes when I've got it running. Yeah, it's starting to look a little bit Heath Robinson, but that's okay. It's just a experimental rig, so that doesn't matter. Yeah, I think I'm going to paint these now. Another update, I've mounted the brushes from the Ford Transit van onto the end here, and I've commoned them up with these 2 cables. This is 350 amp wire, which I've bolted onto the top 2 brushes, and another 350 amp piece of wire onto the bottom 2. I've just used a big bolt there to connect those wires, and then they're both then connected to this cable here. So that's your negative terminal then. So hopefully this is capable of carrying 350 amps out of there. And you'll notice here I've got the shaft in there, so if I turn that around you can see it's turning around with the brushes in there. Alright, I'm just going to start it up, run it at a slow speed. So that's running just over 1000 RPM, and you can see it's drawing 160 watts. Just zoom in on that. 158 watts. Right, if I increase the speed a bit more, (200 up, 2000 RPM), it's just over 200 watts. Right, now we saw earlier that the bearings and the power supply were taking 60 watts. So half the power of the motor is being consumed in overcoming the friction of the bearings and these brushes. And we haven't even got the disc brushes fitted yet, and I would imagine that they're going to generate more friction. So it's probably going to push it over 400 watts, and that's the power of the motor. So I'm pretty sure I'm going to need a more powerful motor, and I saw one online, really cheap, 1.5 kilowatts. And it's a very similar motor to this one, so that's nearly 4 times as powerful, and it does all the same stuff. It's got a speed controller, so I've ordered that. And the good thing is it's not much bigger than this motor, so it should fit on the mounting block. So there's not too much adjustment there. I'll point out a few other things that I've done. I've added some shims to the bearing and the motor just to make sure everything's level. And the other thing was these brush holders, they were catching, so I've just cut a hole in, just cut a slot in there so that they can go further down. I'll get the load bank built next, and still waiting for the super strong magnets to arrive. They should be here in about a week's time. I can't wait to get them spinning around on this shaft. Today I've been working on the control box, which I mentioned in a previous video. Now that I know which motor I'm going to be using, I know what controls can go on here. So I've cut all of the cutouts for the various things that are going to be on here. So we're going to have, this is a 0 to 5 volts voltmeter, that's going to go on there. Slot that in. This is another voltmeter, which is going to measure the generator voltage, because obviously the output voltage is extremely important parameter in all of this. What voltage is this homopolar generator going to make? And I like to have an analog meter because it gives you a very instantaneous visualization of the voltage output. This will take it down to 3 decimal places of millivolts, so they're measuring the same thing. In here will be the power meter that I showed you in the previous video, and we've got the large power switches which are going to go here. Yeah, like that. So they will. There's 2 of them going to go in there, and what you'll be able to do with these is connect the load to the motor all in one go. These 2 switches will carry 200 amps each. The output from the generator will be a negative terminal go on there, positive terminal go on there, and then that terminal, the positive, will go through these 2 switches, and then it will go out. The output will be on that terminal there. So the load bank will go between that terminal and that terminal. And with this new motor that I've ordered, you can start and stop it remotely. So I've put some switches in there. So that's going to be the speed controller now. That's a 10 turn potentiometer, right? That's going to go on there now. So you have to turn that 10 times to go from 0 to full, which will give you very fine control over the speed. So what I'm going to do is, because I'm monitoring the power of the whole thing, the mains needs to come into this box. So I've got a double kettle lead there. The mains power will come in there, and then I'll feed the mains power out to feed the motor inverter, the power supply that drives the motor. But obviously, because I'm taking the power in, I'll be able to monitor how many watts is being used. That connector there, what I'm going to do is I'm going to take all of the cables from the motor control unit and put them in there, and then the 3 that drive the motor are going to come out here. So there's a plug, so there'll be 3 wires coming out of there. So that'll connect the motor, and this connects the motor control unit, which comes with the motor. When we've got these terminals on there, what's going to happen is the wire will come onto there, and then it'll go inside the unit there to the two switches. Hopefully I'll have this finished in the next few hours, and then I can wire it all up. Alright, here's the new control box, and I think it's going to sit probably about there when the generator's running. As I said, that's your negative terminal. That's going to go on there and then go off to the load bank. There's going to be cables coming off each of the brushes, going onto that terminal there. So there'll be 3 cables coming onto that one. That'll go into the control box, through these switches, and then out through that one. Yeah, looks like a real control panel now. That's our speed controller. Switches. I haven't done any of the wiring yet. That's next to do. Right, I've got the control box just about finished. Now, one thing I've done is I've taken the rotor off, because the new motor which has arrived, the spindle is only 7mm and that's 10, so I'm going to have to get this turned down to 7mm. So I've wired the control box to the new control unit for the motor, and this control unit made in China, there's all sorts of parameters you can change in it. You can change how fast the thing comes up to speed, you can change, there's all sorts, generally to do with speed, and this new motor actually goes up to 24,000 RPM, 400 Hertz, and I was farting about with it yesterday, and I accidentally set it onto that setting, and it whizzed up to 24,000 RPM. Wow. Anyway, I'll switch it on. Alright, so we can see the control box lights up, and so these 2 instruments are just voltmeters. They're going to measure the output of the generator, and I can give that a little quick test with this 1.5 volt battery. If I just put this across there, you see 1.57 volts. Now that bottom voltmeter, it only goes up to 2 volts, because I'm not expecting more than 2 volts out of this. You can see that the analog meter has gone up to 1.5 volts as well. So if by some miracle I did get over 2 volts out of it, then we've always got the analog meter. You can see here on the power meter, this control box is only drawing 3 watts, which is good. It's not drawing much power, because, as I said, I've got the power for this, and the motor has been wired through here so I can monitor the power. So flashing there on the display, that's the speed, so 94 Hertz I think that is. Now you can control this control box with external controls, and I've wired them all up, but I haven't got it working yet. It comes with this little manual, which is like with tiny little print in it, which I was reading that last night. I still haven't got it working yet, so that the speed and the controls, as I said, can be operated from this panel. The reason why I've done it like this is so that, because obviously if you build something like this and you've got voltmeters, power meters, all different, like the load, for example, all around your desk, if you want to move it, it's not very portable. I've tried to make it modular, all right, with various types of universal connectors, so that it can be unplugged, so that the generator can be moved, the control box can be moved, and it'll unplug, and you can take it anywhere you like then. All right, so I'll run the motor. So if I hit run there, just make sure it's not set to 24,000 RPM. Right, so there you can hear the motor started up there. As you can see, it's quite a bit beefier, and I'm hopeful that that's going to be able to drive our discs. So that's where I'm at with it really. I'm just waiting for the magnets to arrive, and this terminal will connect to the brushes, and I've got a big crimping tool to make them with. Something else that I've made is these two Perspex spacers. So I went online and I got two 60mm spacers, which are exactly 15mm thick, and I've had holes cut in them, and I've just hacksawed down there. And what they're for is when I mount the magnets, there's an exact 15mm space between the magnets and the bearings. So what I'm going to do is these just push onto the shaft, just clip on there, one for each of the two different diameters. So the magnet will sit, I'll just clip that on, and they will allow me to line it all up so that the spaces are correct. And then once it's all bolted in position, then I can pull these spaces off. It's just going to, and it will also prevent the magnets from, trying to stick to the steel on the inside of the bearings as well. Whoops! Did anyone spot the deliberate mistake? The cable that was on here should have been on here. I had the lead coming in, going to that terminal and going straight out, so there was no actual switch in there. Alright, it's corrected now. What a schoolboy error. I'm just having to tidy up at the minute because, as you can imagine, the house has become like a workshop and there's just bits everywhere, tools lying around everywhere. I just thought I'd point out this spanner set. I bought that when I was 17 years old, so this is 40 years old. Every spanner is still in there. I tell you what, I've had some use out of that. So if you're a young person and wondering whether you should invest in a tool or whatever, do it, because you'll use it for your whole life. Today I've been making the load banks. There's going to be two the same as this, and on it we've got 10 resistors mounted on heat sinks, and these are all going to be in parallel, and they are 0.1 ohm resistors. So let's just say the generator puts out 1 volt and we activate one of the resistors. That's going to draw a current of 10 amps, which will put a 10 watt load on the motor. And what we can do with this is gradually increase the load 10 watts at a time. Or what we could do is put them all on, put the main circuit breaker off, switch them all on, and then immediately add a 100 watt load. So it gives us control over how much load we're putting onto the system. Like I say, I'm making 2 of these. So that's the positive terminal. This is another positive terminal. So I've got four 100 amp cables coming from the generator. So 4 positive terminals. This is 100 amp wire, which I've commoned all these resistors up here rather than try and wire to them individually. I've just done that, and just turn it over. Similar along the bottom here. So everything is rated accordingly. So for example, so if miraculously the generator produced 3 volts and we put one of these across it, this would create a current of 30 amps in these resistors. So that's 3 volts at 30 amps, that's 90 watts. So these are rated at 100 watts. So that's why I've chosen this size resistor, just in case we do get a higher voltage. It may be that if the generator only produces a tiny voltage, I might have to reduce these, but I think they're in the right ballpark. This one is under construction. Yeah, I ran out of solder, and I ran out of something else as well. I ran out of the 100 amp cable, so I've got some of that ordered, and yeah. So this one should have that finished once the parts arrive. Right, I've moved the generator again because it was getting right on my nerves. It was getting in the way when I'm trying to build stuff. So we're in the studio now, and I managed to get these controls working with the inverter control unit. So I'll just show you that. You can probably hear the motor, but I don't know whether you can see it. I'll give a close-up in a minute. And this is our 10-turn speed controller with, as I said, this speed controller here, 1 turn, and then you right up to 24,000 RPM. But with this one, because it's 10-turn, it gives a very fine adjustment. So we're running 100 hertz on there is that's 6,000 RPM it's going at there. So about okay. Now it's important to note that the value on that screen of hertz, that's not the actual speed of the motor. That's the requested speed. That's the speed that you're asking it to go at, which would normally be close to the actual speed. Obviously, if you suddenly increase it like that, it takes a little while to catch up. So for that reason, I've got myself a frequency meter. So what you do is you just point this at this. There's a laser. You point it at the shaft, and that will give you a reading in RPM. So this will